I wanted to go over the Stat 201 component of what you can expect to see in the THEC exam, because for most of us it's been really quite a while since we sat through that material. Now, the good news is that most of that material has been revisited in later classes like BAS 320 and even BAS 471, but it's worth going over and mentioning some of the highlights. Now, Stat 201 isn't a big component of what you'll find on the THEC, and it's all multiple choice, so you'll probably do well on it. But let's dive in and review some of the key points that were more or less Stat 201 specific and didn't get addressed too much in future classes. So overall, the topic of Stat 201 is descriptive analytics. We have a data set, and what can we do to describe the story the data is trying to tell us? What visualizations, summarizations can we make about individual quantities and associations between quantities? So the first thing that we really started out with, was the different types of data that we might have in our data set. And broadly, we split this up into three overall categories. The first type of data that we discuss is a quantitative variable, and a quantitative variable is a type of data that is inherently numerical. It's something that typically has units, and there's no real other way else to measure it except for with some sort of number. So something like height and weight, temperature, counts, quantity, things that you would measure with some sort of device or maybe count up with your fingers, those are the quantitative variables. And on the other hand, we had the categorical variables, or sometimes referred to as qualitative variables. And these are quantities that could vary from individual to individual, but they're not necessarily numerical. The best way to describe them really is with a short text description. So if you were to ask someone's favorite color or what their state of origin was, these would be quantities that are categorical variables because there's just nothing numerical about them. Essentially, the possible values that we might observe are just categories of some sort of quantity. Now, you always did have to be on the lookout for numerical quantities that are really disguising themselves as categorical variables. A variable like an area code, well, the number doesn't inherently tell us anything important about the quantity. The area code is really just a possible category of this area code variable. So I grew up with area code 206. We have 865 here in Knoxville, but in general, those numbers don't really mean anything. They're not measuring any sort of quantity. So we would refer to as area code as a categorical variable because the numbers that constitute it don't really have any special meaning. And this also applies to other types of numerical variables, like your student ID number or social security number, phone number. That's what we refer to as identifier variables, variables that are simply just a way for us to refer uniquely to individuals in the data set. So each data set in the data that the UT Development Office has on each of the different alumni, each alumnus would have a separate identifier variable value associated with them. Your social security number is a identifier variable that the government uses to refer to you. If you go order something on Amazon, each order is going to have a unique order number as well. And those values don't have any inherent meaning either. They're just used to identify the entity that appears in the data set. So in Stat 201, it was very important for us to distinguish between these three different types of data because the way that we analyze it, the types of visualizations and the types of summaries that we make for them are very different. And by now, most of us are actually pretty comfortable with the way that we would summarize a quantitative variable, something that's numerical. We might measure something like an average or a median. If we were going to visualize it, we'd make a box plot or a histogram. With categorical variables, we might make bar charts or a frequency table. But back then, when you were learning it the first time, it took a little bit of getting used to just figure out, well, which of those two worlds were you living in? We typically didn't do any sort of analysis on an identifier variable because those values didn't have any real meaning. They were just used to identify the entities in the data. Now, there was a bit of a complication because especially in business analytics, we tend to jump between both of those worlds whenever it makes our lives a little bit easier in terms of visualization or summarization. So I might have a quantitative variable, something that's inherently numerical, but I might end up making a set of groups to represent the values. One variable I might have in the data is, say, a customer's age, and I might not be interested in treating that as, a quantity in and of itself. 18 versus 19 versus 20 might not be the most interesting thing for me to treat separately. I might group them together into possible categories, like below 18, 18 through 30, 30 to 45, 45 to 60, etc. This is pretty common when it comes to, advertising and marketing. If you're interested in working for analytics for a TV firm, they're really interested in a particular demographic age range. And an age range, a demographic like that, would be kind of a categorical variable because now an age range is like a category instead of something that has a specific numerical value associated with it. It's more like a range of values. So sometimes we have an inherently numerical object, but we're going to treat it as a categorical variable anyway, because it's a lot easier to just group various values together that are related or that make sense or that contribute to our analysis. And we might go the other way as well. If you are in marketing, you might conduct a lot of market research. So you might have someone watch a commercial and then share their opinion on how much they would be interested in buying that product. Or after, say, a political commercial, you might ask how much they agreed with the candidate's position. And so many things are measured on a Likert scale, maybe a 5-point scale, various feeling intensities. And we might have possible values like strongly agree, disagree, neither agree or disagree, agree and strongly agree. And since these have some sort of inherent ordering to them, they kind of slowly go from one extreme to the other, you could potentially get away actually by treating these as numerical variables like 5, 4, 3, 2, 1, or maybe 2 or -2, -1, 0, etc., etc. I'm noticing a typo on my slide here. This should be strongly disagree, then a -2, a -1, a 0, a 1, and a 2 might make a valid encoding. So in business analytics, when we look at the raw data, you should be able to quickly identify what type of variable that you're working with. Is it a quantitative variable? Is it a categorical variable, a factor, as R likes to call it? And then you can decide on your own, well, what's going to be easiest to treat this variable as in order to do the analytics. We might make groups and actually convert a numerical variable to a categorical variable, or vice versa when it makes sense, as long as those categories have a natural and sensible ordering to them. So once we've made that decision, what's the story that we want to tell? Well, we want to come up with a visualization and some sort of numerical summary of the variable that we've honed our interest in on. So starting out with categorical data, what do we do with a categorical variable to summarize it? Well, there's not much that we can really do with categorical data. This one is actually fairly straightforward. One way to numerically summarize the distribution of categories of a categorical variable is to make a frequency table. Just come up with a list of the possible values. We call the possible values of a categorical variable the levels of that variable, and tell us how often each one of those levels appear, either in terms of raw counts or as percentages. And then you can easily make a bar chart to visualize that distribution to pick out the more commonly appearing categories, the less commonly appearing categories, etc. So, for example, way back almost 10 years ago, we gave a survey to all Stat 201 students, and one of the questions that we asked them was, hey, list your favorite alcohol. It wasn't a trick question, even though most of the students were less than 21. We were just curious about the results. Everything was anonymous anyway. And so if we were to summarize the responses, well, there were 4 possible choices that the answers were split into, either beer, liquor, none, or wine. And so a nice way to numerically summarize the distribution of responses is with that frequency table, the list of possible values and their respective frequencies, the counts in the data itself, or to turn those counts into percentages. So 26.6% listed beer as their favorite alcoholic drink. It looks like 11.8% listed wine as their favorite alcoholic drink. And sometimes the numbers are nice to have, but very often a picture is worth more than a big old long table of values. And so when we summarize, visually at least, the distribution of a categorical variable, the bar chart is really our go-to. We don't really use pie charts in analytics. Pie charts are still all over the place, but best practices in visualization say that you should probably avoid these. And so all we would do is just to create a bar for each one of the different categories, make sure the widths of those bars are equal across every single different group, and then have the height of the bar either go up to the raw count of the number of times we saw that value in the data, or maybe have the bar go up to the percentage of the responses in that category in the data. So once we have that, well, what can we do to describe the distribution? What things do we focus in on with that distribution? Well, one thing that we talk about is the mode of the distribution. So which value or which category most frequently occurs in the data. So the mode for the favorite alcohol distribution is liquor, because that was the one that was most frequently listed. And we might talk about the least frequently occurring value as well. There's not a special name for that in analytics. In this case, wine is the least commonly occurring value, but there's really not all that much else we can talk about with the distribution of a categorical variable. The mode, the most common, the least common, just relative rankings of how often we see each of these categories. Relatively limited, right? Fairly straightforward here. Now, if we are dealing with a inherently numerical quantity, a quantitative variable, what do we do to summarize its distribution? How could we talk about it numerically, and what sort of graphics are useful for summarizing that distribution? So another question we asked those Stat 201 students was, how fast have you ever driven while you've been the driver of a car? Well, if we ask for just a summary in R of what the values in that column was in the data set, we'd be presented with what we refer to as the 5-number summary, and then actually some additional information that R likes to tell us, including the number of missing values, the number of NAs in the column of data. So what is this 5-number summary? Well, the 5-number summary includes the minimum value in the data, 50 miles per hour in this case, the maximum value in the data, 210 miles per hour, the median, basically the midpoint if we were to sort the values from smallest up to biggest. The median value is 100, half the values are smaller, half the values are bigger, and then also the first quantile and the third quantile. So I wish that this was labeled a little bit differently, because the first quantile is really just the 25th percentile, in this case 90 miles per hour. The 25th percentile, or first quantile, lets us know that 25% of data values are less than 90. 75% must be bigger than 90 then. And the third quantile, well, that's the 75th percentile. 75% of the responses to this question were less than 110. 25% must have been greater than that. So we get an idea over how the responses vary from smallest up to largest. We get a measure of the typical response in terms of its median. And R is nice because it also lets you know what the average value was. The average, the mean, those are two words that are synonymous. The average value is another way to summarize a typical value in a distribution. The average speed, as recorded in this data, was 102.4 miles per hour. And so one question that we ask ourselves very often in business analytics is, since we do have a choice for how to summarize a typical distribution we might see in a set of data, which one do we choose? Do we choose the median, or do we choose the average or mean here? And to know which one is the most appropriate, we actually need to make a visualization of that distribution, because one is more appropriate than the other depending on the shape. So a couple different ways to visualize the shape of the distribution of a quantitative variable. The one that I think we're the most used to looking at is a histogram. And actually, to tie this back into a little bit earlier in the discussion, a histogram actually takes that distribution of numerical values and comes up with a set of categories to represent it. So each bar is essentially lumping together a range of values into a common category, and it's presenting the results like a bar chart. So this bar right here, whose left edge is at 100, whose right edge looks like it's right at about 110 here, represents the total number of individuals in the data that responded with a value somewhere between 100 and 110. So when we look at a histogram, well, what do we talk about when we look at the shape of the distribution? Well, the first thing that we look at is the number of peaks, what we refer to as the number of modes of a distribution, and where they're located. In this case, we just have a unimodal distribution because there's a single peak. If there were two peaks, we would call it bimodal. If there was more than two peaks, we'd call it multimodal. Trimodal if there were three here. So one thing we like to talk about is, well, where is the data most concentrated? Where are the peaks of the histogram, or the modes of the histogram here? Most distributions in business analytics are unimodal, like this one right here, but it's always worth looking at a picture to see how many modes we're dealing with. Once we've talked about the number of peaks, we can talk about whether or not there are any gaps in the data as well. Are there any values where, for whatever reason, we just don't see many data values there? Now, a gap is actually related to the peaks of a distribution. Gaps really separate peaks here. With a unimodal distribution, there's no gap, there's just a nice gentle fall off in the frequency towards larger or towards smaller values here. If I were to look at the Old Faithful data set, this is one of my favorite data sets to look at. If I bring up the Old Faithful data set, if you've ever been to Yellowstone or plan to go to Yellowstone, you want to go see the Old Faithful geyser. And it turns out that the eruption times of the Old Faithful geyser have this bimodal property. If I print them out, not very useful. We want to visualize this here. So if we make a histogram of the eruption times, we see something that's bimodal. Roughly half the time, we get an eruption that lasts right at around 2 minutes. About the other half the time, we get an eruption that's a bit longer, a little bit over 4 minutes here. There's, for whatever reason, some sort of gap between these two peaks. It looks like that times that are maybe 2 3/4 of a minute, those are relatively rare. So first thing that we do when we look at that histogram, we say, okay, how many peaks does it have? There's more than one peak, then where are the gaps as well? Where is the data relatively rare? When we do have a unimodal distribution, then we talk about, well, how symmetric or how skewed is that distribution? Symmetric means that as we look to the left-hand side of the peak and to the right-hand side of the peak, we see roughly the same shape. This would be an example of a skewed distribution because the two halves here, to the left and to the right of the peak, don't really match up all that great. When we do have a skew, we add some additional information as to whether or not it's skewed towards the right or skewed towards the left. So how do we tell the difference? Well, we look to see, well, where do we find that gentle decrease in the frequency of values? If we see kind of a slow, gentle decrease off towards larger values, off towards the right of the peak, that's when we say that we're dealing with a right-handed skew. If, on the other hand, we had that slow, gentle fall off towards the left of the peak, we would say that we had a left skew here. So, can I make a left skew distribution? Let's put my skills to the test here. Let me see if I draw a curve of a probability distribution we've used quite a bit in BAS 471, the beta distribution. Let's see if my memory serves me well. Nope, got that wrong. Let me switch these two numbers. This would be a right skew distribution because there's actually nothing to the left of the peak. We got that slow, gentle falling off of values towards the right of the peak. If I change this up just a little bit though, watch what happens. So here I would have a left skew distribution because there's actually nothing to the right-hand side of the peak. We get that slow, gentle fall off of values towards smaller and smaller values towards the left of the peak. Let me see if I can do a little bit of a better job here. I'll do some trial and error. Here's an example of a left skew distribution. Notice that we do have something to the left and to the right of the peak. It falls off towards values much more quickly towards the right than towards the left. We have a much more gentle fall off of values to the left here. So back in BS 471, that notorious zoo, that Weibull distribution was one of the few distributions that gave that left skew. That's relatively rare to see in business analytics. Most things we see are unimodal with a right-handed skew here, that slow, gradual decrease in frequencies as we move up towards larger and larger values. So the last thing that we like to discuss with the distribution of numerical data is whether or not we have outliers, individuals that are so far removed from the peak that they're kind of unusual. And with this distribution of fastest speed ever driven, we can see that we do have these two little tiny bars that are very far separated from the peak up towards very large values, up over 200 and in the 180 or so range. So not many data values there, maybe one or two individuals that have separated themselves from the rest of the pack. We call those outliers. So those could be mistakes in the data in recording. These could be just lies that the Stat 201 students gave. They're not taking it seriously. They're just putting in some random numbers. Or it just might represent extraordinary situations. You never know when you're going to have a Stat 201 student who also is a race car driver. These values that are very large could be legitimate. Very often, those outliers are the most interesting data points you have in your data set. What makes those individuals so unique? So, summarizing our distribution of fastest speed, what would we say? Well, it's unimodal, there's no gaps or anything, and it is skewed towards the right. So skewed towards the right means that it is that slow, gradual decrease towards larger values. And we do have some outliers up at very large numbers here. A little over 200, a little bit less than 200 here. Definitely some unusual values. Now, I need to tie this back in to what we were just talking about. What number do we actually use to summarize the typical value in a data set? Well, it's tied into the shape of the distribution. And whenever we have a skewed distribution, like fastest speed ever achieved, that's when we want to use the median value, the value where half the values are above, half the values are smaller. The average value we're only going to use as our summary when we're dealing with a roughly symmetric distribution. So why is that the case, actually? Understanding this choice between the mean and the median is actually a pretty important concept in analytics. I'm going to come back to the box plot in a second because I want to talk about why it makes sense to use the median when we're dealing with the skewed distribution and why it's okay to use the average if we have a symmetric distribution. So almost everything in business analytics, when we make a histogram, we get a distribution like this, described by the black curve. We have a unimodal distribution skewed towards the right because we have that slow, gradual drop-off in frequency towards larger values. Something that we see all the time. Fastest speed, amounts purchased, the time spent on some sort of task. We see this all over the place in business analytics. Now, if you were to just look at this curve, and if you were to answer the question, well, what's the single value that best summarizes this distribution? You might be tempted to say, well, whatever this value is right at the peak, technically the mode of the distribution. But it turns out that for numerical data, it's actually very difficult to measure where the mode is. With a categorical variable, super easy. You just see which category appears most in the data. But if you're dealing with a quantitative variable, it might be the case that all values are unique. So there is technically no mode. You can make some visualization of what that distribution looks like, and it's going to peak somewhere, but that's actually a very difficult thing to really write down. Where is the absolute peak of that distribution? However, I think most of us would agree that, yeah, a value that's close to the peak really serves as the best summary of what a typical value of a numerical distribution would be. And so that's going to help in our guidance for why it makes sense to use the median for skewed distributions and why it's perfectly fine to use the average, but only for symmetric distributions. So I've drawn a vertical line in blue and red representing the median and the mean of this distribution. And what you'll notice is that the median, it's not quite at the peak, but it's closer to the peak than where the average is. What's happened is that since the average is, just taking a weighted sum of all of the values that we've observed in the data, giving each value actually equal weight, these really large values, kind of very far away from the peak, are dragging the value of the mean up towards it. One thing you might remember about outliers is that outliers can vastly influence the value of the mean because the mean uses information from every single data point in the data set in its calculation. So with a skewed distribution, the mean is always going to be dragged up towards wherever that skew is located. we have a long right tail, so a gradual drop off towards larger values. That mean is going to be dragged up a little bit towards a larger value as well. The median is what we refer to as being a bit more robust, not as sensitive to the specific values that we find in the dataset, less sensitive to outliers here. And so that's why, at least I think, it always makes sense to use the median to describe a typical value instead of the average or the mean when we're dealing with a skewed distribution. Now, if we do have something that's perfectly symmetric, well, it turns out the mean and the median are both going to be in the same place. Like if we make a curve that represents the normal distribution, our favorite bell curve here, I'm going to make it have an average of 5 and a standard deviation of 2 here. If we look at the distribution and we have symmetry, well, the mode, right where the peak is exactly where the average is. And in fact, that's exactly where the median is as well, because half the values are going to be smaller and half the values are going to be bigger. And so that actually raises a fairly interesting point, is that if we are dealing with a symmetric distribution, the mean and the median are identical, and if we're dealing with a skewed distribution, the median is definitely the preferred summary, why don't we always just use the median as our summary of a typical value? And that's actually a really deep and insightful question to ask. And the answer, I think, depends on who you're going to talk to. If you talk to someone that learned about statistics and probability back last century, well, they'll have a very different answer than someone who's studying analytics right now. In my opinion, and this isn't universally shared, I think it's always okay in analytics to just summarize a typical value of a distribution with the median, because it's always going to be appropriate no matter what the distribution looks like. Why people still insist that the average is a better summary of a distribution when it's symmetric deals with the whole job of inferring what the average is of the probability distribution that's generating the data, that mu parameter that we've discussed in our discussion about probability distributions. If you want to estimate mu, the average of that probability distribution that's making the data, then statistically the sample average gets a little bit closer typically to what that true value of mu is than what the median does. And so the reason that there's still an argument for using the average versus the median is that maybe that's what you want to do. Maybe you want to estimate what mu is of whatever probability distribution is making that data. But I think for the most part, as business analytics practitioners, we just have a data set and a set of questions. We don't really care what that probability distribution is. We don't necessarily need to know the mu parameter, the average parameter. We just want to come up with a typical value of the data to share with the boss. And so I think in this case, the median is always going to be okay, even if it's roughly symmetric. All right, let me go back to the box plot though, because that's the other way, the complementary visualization to the histogram that we use when we summarize the distribution of a numerical variable. And the box plot can add in some additional information that the histogram has a really difficult time in communicating. So when we look at a histogram, we can pretty easily see where the peak or the mode of the distribution is. But one thing that's fairly difficult is figuring out where the median of that distribution is, which I just said is kind of a safe way to summarize the typical value no matter what the distribution looks like. Well, the box plot has you covered here. So the box plot summarizes the distribution with a box, some whiskers, and maybe some additional dots. This vertical line right here, this center of the box, represents the median of the distribution. So once you look at a box plot, you automatically know that half the values are smaller and half the values are bigger. And you can just use your eyes to figure out about where that median is. So from the histogram, it's kind of difficult to tell exactly, well, what's the average, what's the median. I can tell you the peak is a little bit less than 100, but I can very easily use this box plot to tell you, well, the median speed here is 100. You can use that as your measure of the typical value. Much easier to read off that box plot. It also tells you how concentrated that data is. So the vertical line on the left-hand side of the box and the right-hand side of the box represent the 25th percentiles and the 75th percentiles. Well, by definition, the amount of data that's in between the 25th and 75th percentile is going to be 50%. So one thing we know is that half of the data values are going to live inside the box. So we have an idea for how concentrated the values are, the range over which values are kind of clustered about, and that's some information that we can kind of eyeball from the histogram, but it's difficult to just read that off. We can kind of eyeball it and say, well, we have a lot of data between these values here, but it's a little bit loosey-goosey. We have this very well-defined 50% mark that we know are going to be living inside this box. Now, what do the whiskers do in the box plot? Well, they're drawn out to the largest and the smallest, what we refer to as ordinary values of the data. And back in Stat 201, you studied a lot what it meant to be ordinary versus an outlier. We're not going to worry about exactly what that definition is. It's a mathematical construct here. Someone came up with it, thought it was a great idea a long time ago, and it's stuck with it ever since. The thing that we're just going to worry about is using that pre-existing definition in our definition of the box plot and in our interpretation. Basically, anything that it falls inside these whiskers is what we'd refer to as an ordinary value. It's close enough to the peak that it's not that weird. Anything that's beyond these whiskers, anything that gets a dot to represent an individual, is what we'd refer to as an outlier, something that what we would refer to as unusually far away from the peak. And that's another huge strength of the box plot. The box plot tells us, okay, here are the unusual individuals in our data, the ones that are a little bit weirdly high, the ones that are a little bit weirdly low. And that's very difficult to tell just from looking at the histogram. These two outliers here near 200 was easy for us to identify, but there's no formal strict definition of what makes an outlier versus ordinary when we just look at a histogram. That's one of my favorite things about the box plot. It really brings out these unusual, kind of odd points. But the box plot can't be used as our only visualization. The histogram and the box plot are complementary because, well, the histogram can tell you things that the box plot can't. Back to that old faithful data, notice we have this bimodal distribution around 2 minutes and 4 minutes as our peak. That bimodality is completely hidden by the box plot. The box plot isn't designed to show the structure or the shape of the distribution. The box plot's more interested in letting you know, well, what's the midpoint? What's the percentiles? What separates ordinary from being outliers? So we can't see gaps, we can't see peaks in the box plot. That's what the histogram is for, but we definitely learn a lot from the box plot, so we always want to look at these both in tandem. It's not really a choice between these two. Look at them both. They tell different aspects of the story here. All right, so quick summary of the 3 ways that we numerically summarize a distribution. The mode can be applied to both categorical and numerical values. It's essentially the most frequently occurring value in the data, if it's categorical, or where that distribution peaks, if we're talking about numerical data. If we do have numerical data, 2 other measures that we more often use, because they're easier to measure from the data, is the median or the mean. Typical values we might observe from the distribution. The median's nice because half the values are smaller, half the values are bigger. Always safe to use this to summarize the typical value even when the distribution is skewed. The mean is just the average or expected value of that distribution. Really only appropriate for when outliers or skewness isn't tainting the value. That's when we have a nice symmetric distribution. So some pros and cons to both. Definitely review them. We've talked about them during this narration, so I'm not going to say that again. But here's some nice tips for how you decide whether or not you use the mean or the median here. All right, so moving on, a typical value is nice, but we want to push that discussion a little bit further by knowing how clustered the values are around that typical value. If I say the typical amount of money someone spends at a store is $50, that's nice, but I want to know, okay, well, is it $50 give or take 5? Do most people spend almost exactly $50? Or is it $50 give or take 30? There's a fairly wide range of values that people might spend. So we want to know, are values tightly clustered around the average or the median? Or are values kind of uniformly distributed across some range? What's a measure that we can use for the spread of values in a distribution? So for numerical data, this discussion is relevant here, we have a choice. We can either use the standard deviation as our measure of how spread out the values are, or we can use the interquartile range. Let's review the standard deviation. This is something that we've talked a lot about in BAS 471, especially in the context of our favorite probability distribution, at least for statisticians, the normal curve. We like the log normal better for business analytics here. But the normal curve is our bell curve, got that single peak, it's symmetric, and the standard deviation of a normal curve was that very special point where the curve went from sloping downwards faster and faster to sloping outwards. That's the inflection point of the curve, and we had the standard deviation be the distance from the peak to where that inflection point was. All normal curves kind of have that same property where it works out that about 2/3 of the data values are within plus or minus 1 standard deviation. About 95% of data values are within plus or minus 2 standard deviations. Since all normal curves have that property, and since back in the day we loved having symmetric distributions, that's what kind of stuck. So when we talk about the standard deviation of a collection of data values, that's kind of what we're getting at. We're kind of assuming that we're dealing with a symmetric distribution and that the standard deviation is going to do a good job of talking about roughly how far values are away from the average. So I have a special way of how I like interpreting what that standard deviation is, and I think it's worth going over. Now, one data set that's built into R is MT cars. It talks about different properties of cars that were released back in the mid-2000s. One thing that we might want to look at is the fuel efficiency of these cars. Total of 32 cars here. If we ask for the average of this distribution, is that a smart thing to do? Well, always want to check out that shape of the distribution. We can make a hist of the MT cars, $MPG to get the fuel efficiency. It's roughly symmetric, sure. Let's say we can get away with using the average as our summary of a typical value. Well, if that's the case, the average fuel efficiency in the data is right at about 20. So how clustered or how spread out are values around the average? Well, if we ask for the standard deviation of values, we get a value of right at about 6. So how do we interpret this? 2 ways that I like doing it. First way, nice and easy. We can say that the typical value we might observe in the data is around 20, give or take 6 or so. So one way to interpret that standard deviation is the give or take associated with the average value. Another way that I like interpreting it is that the standard deviation is the typical difference between the values in your data and the overall average. So the fact that we're seeing an average of 20, a standard deviation of 6, tells me that typically the observed fuel efficiencies in this data are around 6 miles per gallon or so away from the overall average of 20. And that does a pretty reasonable job here. If the average is right about 20, give or take 6 or so gives us, most of the fuel efficiencies in the data. It's a nice way to talk about how spread out those data values are. Now, the problem is that if we have a lot of outliers, or if we have a very skewed distribution, the standard deviation can be a bit misleading. The standard deviation might be a substantially larger number than really the typical difference between values and the average or the median, and so we might want to reconsider if the standard deviation is going to be appropriate. So when our data set does have outliers, this value of the standard deviation, the value of the mean, are really quite sensitive to that. Throw in one absurdly large value into your data, all of a sudden that throws off the average, it throws off the standard deviation. You can get much larger values for both. So just as an example of that before we go back, let's look at the distribution of the amount of money that people have in their checking accounts. So some people, negative balance, maybe need a little bit of money management there. Some people have a lot of money in their checking account. Maybe they should be investing this stuff, but anywhere from minus $774 up to over $278,000. Now, this person here with all that money in their checking account is an extreme outlier, much, much larger than the typical customer to this bank. Because of the skewed nature of this distribution, just looking at this box plot here, the right whisker is much longer than the left whisker. We have all these little individual dots representing outliers up towards larger values. The median is definitely going to be a much fairer summary of a typical value. The median amount that people have in their checking account is 570. So this 278,000 is way out of line with what the typical value is. And the fact that we have so many of these large outliers, notice what it does to the value of the average of the data. With all of the large outliers, those outliers have dragged the value of the mean up towards a pretty large value, a little over 2,000. Now, what I've done is I've drawn a red vertical line on this box plot to represent where the average value is of the distribution. And you can see that the average does a pretty lousy summary. We just talked about how 50% of the values in the data live inside this box here. So we see that this average is actually above the 75th percentile. More than 75% of the values are below the average. Fewer than 25% are above the average. If you think to yourself, is the average being a good summary of the typical account balance here? No, the answer is no. It's nowhere near the peak or the center of this distribution. So these outliers vastly messing up the kind of reliability of that average to give a good summary of the typical value. And then what I've also done is I've drawn a blue line at +1 standard deviation and -1 standard deviation from the average. Now, when we had that normal curve, when we do have that nice symmetric distribution, about 2/3 of data values fall within ±1 standard deviation. Notice how that's not remotely the case for this data set. Going 1 standard deviation below the average, we get to -$5,000. Well, every single value, even the ones below negative here, are above that. And if we go 1 standard deviation above, we land right at about $1,000 here. There's hardly any data values that are above that. So in this case, the standard deviation would do a pretty lousy job at describing the typical deviation of values from the overall average. ±1 standard deviation encompasses almost every single data value in this data set, instead of the 2/3 that we're kind of hoping that it does if we were dealing with an isometric distribution. So the value of the standard deviation, if we were to measure numerically what it was, it looks like it would be maybe around $7,000 or so. That does not tell us the typical difference between the account balances and the overall typical value here. Most of them are kind of clustered. 50% of the data falls in between the 25th and 75th percentile. Most of the data values we have are between $65 and about $1,800. So standard deviation, terrible job at helping us summarize that distribution. What's the alternative? Well, just mentioned the size of the box here. The alternative is that interquartile range. So the interquartile range is just simply the length or the difference between that 75th percentile and the 25th percentile. So if I took 1,800, subtracted off 65, that one number would tell me essentially how the range of values where 50% of my values are kind of clustered. So one way I like thinking of it is saying that the innermost 50% of the data, basically the 50% of the data points that are closest to the peak, are all within IQR of each other. So the numerical value of the IQR for these account balances, subtracting the 75th percentile and the 25th percentile, works out to be $1,750. What we can say is that the innermost 50% of account balances are all within $1,750 of each other. That gives us a much fairer impression of how closely values are clustered together in the dataset than that standard deviation. So at the end of the day, it's actually pretty easy to just remember which summaries are we using for the distribution. If we have a skewed distribution, like we typically do in business analytics, it's the median and the interquartile range to capture the typical value and then how clustered or how spread out the values are away from that typical value. If we do have a nice, roughly symmetric distribution, the average, the standard deviation, that correspondence with the normal curve is okay to use to describe the typical value, and then how far off we typically find values in the data from the average. So that's how we summarize a distribution of one variable, both numerically and graphically. In business analytics, we're a lot more interested in studying associations between two or more variables. And so you spend a good deal amount of time in Stat 201 and really also in BAS 320 talking about relationships between two or more different quantities. Now, if we had two numerical variables and we wanted to study their relationship, the best visualization is going to be a scatter plot. So let's imagine we wanted to study the relationship between someone's scores on the final exam and their scores on the midterm exam. Each point would represent an individual in the data, and each point is representing a pair of values, their score on the midterm and their score on the final. This one right here looks like they scored right at about 80 on the midterm, a little bit less, about a 60 or so on the final exam. So we have some conventions for what we call both of these different variables. So we say the y variable in our relationship is what appears on the vertical axis. The x variable is what appears on the horizontal axis. And normally the way that we construct the scatter plot is by asking, okay, well, how are we approaching this relationship? Usually one of the values we're kind of interested in predicting from the other. Like in this case, I'd like to predict someone's final exam score from their midterm exam score. And so whichever quantity we want to be predicting, our variable of interest in this case, is going to be our y variable, and that's what we put on the vertical axis. The quantity we're using to make those predictions we'll refer to as the x variable, and that's what we put on the horizontal axis. So we're using someone's score on the midterm to try to predict their score on the final exam. Now, when we have a scatter plot, how do we talk about that relationship? What are some metrics that we focus in on to flesh out what this relationship looks like? Well, the first thing that we talk about is the relationship positive or is it negative? So what separates these two? Well, we look at the stream of points and we look to see, well, what is the trajectory of that stream of points? Is it heading up and to the right, or is it heading down and to the right? So if it's heading up and to the right, well, that means that as the x variable gets larger, we typically find the y variable getting larger for those individuals as well. The two are increasing in tandem or decreasing in tandem, depending on which way our eyes are going across the plot. A negative relationship is the reverse. A negative relationship has the feature when, as one of the variables is getting larger, then the other variable tends to be getting smaller on an individual basis. Here's the relationship between the number of fumbles that a football team loses and the number of wins they have for the season. And not too surprisingly, as we consider teams with more and more fumbles that have been lost, we see that those teams' number of wins is getting smaller. The trajectory of the stream of points is somewhat heading down and to the right, and so we say that's a negative relationship. Here's an example of a positive relationship with a little bit of a curvature to that stream of points, but there's no requirement that a relationship have just one type of direction here. We might actually have parts that are mixed. We might have positive and negative parts, and that's worth talking about. In fact, if you look at the relationship between the fuel efficiency of a gasoline engine and the average speed that the engine is driven at, you would find a mix of positive and negative parts. There's an optimal speed that you can drive to maximize your fuel efficiency. Slower than that, and your fuel efficiency is smaller. Too fast, your fuel efficiency is smaller as well. And in fact, way back in the day, in the 70s, when there was a big oil gasoline crisis, that's when the federal government said, hey, on highways, we need to enforce a speed of 55 miles per hour, because at the time, with engines at the time at least, 55 miles per hour was the place that maximized fuel efficiency and was saving the most amount of gas. Times have changed. There's no reason to keep it at 55 now. That's why things are more like 65 or 75, depending on the state. But back in the day, that's why that was the case. So with a scatter plot, we focus in on the direction of the stream of points. Is it positive, going up and to the right? Are both values increasing together and decreasing together? Is it a positive relationship? Or do we have a negative relationship? As one goes up, the other goes down. The next thing we talk about is the form of the relationship. Is the trajectory well described, at least roughly, by a straight line? like what we have in these first two scatter plots, a positive and negative relationship here? Or does it look like the trajectory is curved? When the trajectory is curved, we call that a nonlinear relationship. Both these scatter plots on the right have curves to the trajectory. And when there is curvature, we follow that up by discussing what type of curvature that we have. Two different flavors. We can either have a monotonic relationship. That means that the trajectory is either always increasing or always decreasing. In other words, the direction is always positive or always negative. A non-monotonic relationship would have mixes of positive and negative parts. So as we see this relationship curving back on itself, this would be an example of a non-monotonic relationship because part of the relationship is positive and part of the relationship is negative here. So some terminology, some lingo that we like using as business analytics practitioners to describe the relationship between two numerical variables. Usually the most important thing and interesting thing to people is how strong that relationship is. Are we talking about two variables that are very closely related, or is there a very weak relationship? If there's a very strong relationship between people's final exam and midterm exam, we wouldn't have to worry about even giving a final. Because if there was a strong relationship, once I knew what your score was on the midterm, I pretty much know what your score is on the final. Sadly, well, good news for business analytics practitioners is that most relationships are kind of weak, so we need some sort of strategy and some sort of approach for how we handle the relationships that are interesting to us. But from a scatter plot at least, how can we tell if we're dealing with a strong or a weak relationship? Well, it's tied into the amount of vertical scatter that we see in the stream of points. So the more vertical scatter, the more variety that we see in y values at a particular value of x, the weaker that relationship. What's a good way to think about it? Well, I like thinking about it as, well, how much could we narrow down the possible values of y that we might observe once we know an individual's value of x? If we can narrow it down quite a lot, that's a very strong relationship. Once we know x, we kind of know y. And if we can narrow the y value down by quite a bit, well, that implies that there's not too much vertical scatter in the individual's y values when we focus in on a particular value of x. This one over here would be a strong relationship because once we know what their x value is, there's really not that much variation in y. There's very little vertical scatter. The relationship on the left, we have a very, very weak relationship. The amount of vertical scatter that we see is basically the same no matter what the value of x is. No matter what value of x we focus in on, the y values are all roughly between 8 and 12. For this strong relationship, well, if I knew x was 0, then y is right at about 1. If I knew x was equal to 1, I know my y value would be right at around 1.9. So how strong is that relationship? How much vertical scatter do we see? Now, one important point, especially in Stat 201 and BAS 320, was making sure that we were crystal clear on some of the terminology that we use quite a bit in analytics. Now, in everyday lingo, we talk about correlations as an appropriate term for just describing any generic relationship under the sun. In analytics, that's not really quite the case. Correlation is actually reserved to describe the strength of a linear relationship between two numerical variables. So we wouldn't actually use correlation to describe the strength of this curved relationship here. We wouldn't use correlation to describe the strength of this curved relationship here. Correlation technically is only useful for describing relationships like this, where we have a linear trajectory in the stream of points. The numerical value of the correlation, the closer to 1 or minus 1, the sign of it's tied into the direction of that relationship, the stronger that relationship is. The closer to 0, the weaker the relationship, the weaker the correlation. The farther away from 0, the stronger that relationship. If we're just going to talk about relationships in general in business analytics, we talk about associations. That's our general word for describing relationships in analytics, and that can apply to both linear, nonlinear relationships. It can apply to relationships between categorical variables. So we know hair color and eye color have a pretty strong relationship. They're not correlated technically because they're not numerical quantities, but we would say they have a strong association because once you know one, you've narrowed down the possible values for the other quantity pretty well. All right, so back to correlation in itself, we have a special symbol for it in statistics and in analytics. That's little r. And that's going to be used to describe the strength of the relationship. So a value of 0 means they're not correlated. Basically, once we know x, that doesn't really tell us anything that we can really say about their y values. There's no correlation between those two quantities. The farther away from 0 we get, either positive or negative, the progressively stronger of a relationship that we're dealing with. Best visualized here. Here's a nice scatter plot where we have no correlation whatsoever. So technically it's a linear relationship because any line would actually do equally a good job of describing the trajectory here. There's no curvature. But this has a correlation of 0 because really you don't narrow down what the y value is once you know what x is. There's equal vertical scatter, equal range of y values no matter where you look. On the other hand, here we have a pretty strong correlation. The numerical value turns out to be right at about 0.9 here. We see that the ellipse here that's describing this trajectory is pretty flat. The flatter that ellipse, the stronger the correlation. So you can see the more scatter, the closer that correlation value is toward 0. Negative when we have a negative relationship, positive when we have a positive relationship. So keynote is, because correlation is a value reserved only for linear relationships, we always want to be careful not to overinterpret the value of the correlation for just any two random numerical quantities. It's very possible to have a strong relationship between x and y, two numerical quantities, but have a correlation of 0 when the relationship is just simply not linear. So here's a perfectly well-defined relationship between x and y. All the points fall exactly on a parabola here, but the correlation is still 0 because there's no linear component to this relationship. Here we have a nice tight circular relationship going on. Once I know x, I can definitely narrow down what the possible values of y are, but numerically the correlation works out to be 0, etc. For examples where there's no linear component to the relationship, and so the correlation is 0, but they're still fairly strongly associated. All right, so what do we do if we're measuring the strength of a relationship between two categorical variables, like that hair color and that eye color? Well, a scatter plot's not going to work because they're not numerical values. What do you do instead? Well, we make a mosaic plot. So a mosaic plot is simply side-by-side segmented bar charts. A bar chart is just giving us the percentage of different categories that we find in one level of our grouping variable. So for instance, let's imagine that I'm studying the click-through rate of different ad designs. So I have two designs here, position 1 and position 2. So banner position is one of my two categorical variables. And then the outcome of each visit is either a click, yes, or a no. So two categorical variables. I want to know how strong of an association is there between these two. The stronger the association, the more evidence that I would have that one design is better than the other. And so a mosaic plot is going to help me visualize this association as follows. I essentially make one bar chart for the banner position in position 1, another segmented bar chart for position 2, and then I simply split up the area inside each one of these bars to the proportion of yeses and nos that I have. So what do I end up seeing? It looks like position 2 is the better one because more of its area is color-coded red. A higher proportion of visits for ads that were in position 2 resulted in a click. So the bigger the difference that I see among these segmented bar charts, the stronger the association. I don't really have a number like the correlation that I can use to describe the strength. It's more of a visual thing here. So another example with click-through rates, imagine I did an experiment where I was keeping track of what device the ad was viewed on. So people have iPhones and different models of iPhones. They might have different phones that run on the Android operating system. There's a bunch of different devices, including laptops, desktops, Mac, PC, etc., etc. This ad might have been viewed on. And so I might be interested in studying, well, is there an association between clicking on that ad and the device on which that ad was viewed? If there was, well, then there might be certain devices that I want to make sure to have that ad being displayed on because the click-through rate's high. And conversely, there might be devices where the click-through rate is relatively small. So here would be my mosaic plot for this situation. I would have a segmented bar chart for each one of the devices in my study, D1 through D18 in this case, and then I would simply shade the region in each of these segmented bar chart according to the outcomes of that visit, the yes or the no. So I see a pretty big difference as I compare the segmented bar charts from one category to another. I would say that this has a moderately strong association. Here's another example of a moderately strong association. Here we're comparing drop call frequencies in terms of rarely, often, and occasionally across different carriers, AT&T, Sprint, US Cellular, and Verizon. We see that these segmented bar charts look really quite a bit different. Specifically, if we were to focus in on Verizon, we rarely see drop calls among the individuals in the study, whereas AT&T, the fraction of individuals that rarely had drop calls is substantially smaller. In fact, the proportion of AT&T customers with occasional drop calls is much bigger than the other carriers here. We do see big differences in the distributions across the different carriers, indicating that the association between drop call frequency and carrier is pretty strong in this case. What's an example of a weak association? Well, we could go back to the Stat 201 student survey and look to see if there's any sort of an association between the gender of the student, measured as either male or female, and where they typically sit in the classroom, either in the back, in the front, somewhere in the middle, or it varies every time. In this case, if we look to see how the responses break down for each gender, we don't really see too much of a difference. About the same percentage of females sit in the back as the percentage of males. About the same percentage of females had varies as males. The areas of each one of these categories here, front, middle, back, and varies, is just about the same between males and females. So it doesn't look like there's much of an association going on. It looks like the distribution of seating location is just about the same regardless of gender here. So a nice useful slide for just pointing out, well, what do we look for in a mosaic plot to determine if there's a weak or a strong association? It's basically just looking to see if the shadings of all the bars are more or less the same. The bigger the difference, the stronger the association here. And that'll conclude the overview of the Stat 201 content for the THEC exam. There's that YouTube video that I had made last semester that covers the BAS 320 content. So if you'd like to review some BAS 320 material, and you probably should, it's a little bit rusty. There are a lot of really kind of key details that the THEC covers. Definitely head on over to that YouTube video.